This is a report of Professor Christian Budde. Please.
Christian Budde.
Christian Budde. Thank you, Christian Budde. Please, you can start your report.
Thank you very much. First of all, I want to thank the organizers that I have the opportunity to contribute to this nice conference on one-parameter semigroups of operators. And today I want to contribute with my talk about positive Miyadera-Voigt perturbations of bicontinuous semigroups. And yeah, my talk is structured in three parts. First, I want to give a motivation for bicontinuous semigroups. Then I will talk about positivity and perturbations. And at the end, I hope there's enough time, I want to talk about an example on the space of bound problem measures. Okay, let's start. A motivating example for bicontinuous semigroups. Consider the space of bounded continuous functions on Rn and the following differential operator with a really nice domain. It's a differential operator. And then we consider the corresponding abstract Cauchy problem. And it can be shown that for each initial bounded continuous function, there exists a solution. And moreover, this solution can actually be represented by an operator semigroup. However, it can also be shown that this operator semigroup is not strongly continuous with respect to the supremum norm on CB of Rn. And so one has to think about how can I treat such non-strongly continuous semigroups. And the idea is to work with so-called bicontinuous semigroups. And the setting is as follows. We start with the Banach space X. In the previous examples was the space of bounded continuous functions on Rn. And we add a locally convex topology generated by a family of seminorms, satisfying the following assumptions, which are made by Franziska Kühnemund. She was a PhD student from Rainer Nagel in Tübingen, and she investigated these bicontinuous semigroups first. And the assumptions are as follows. The norm topology is finer than the locally convex topology tau. Secondly, X is sequential complete on norm-bounded sets, which means if I have a norm-bounded and a norm-bounded tau Cauchy sequence, it's tau convergent. And the third assumption is that the dual of X with respect to this locally convex topology is norming for X, meaning that I can express the norm of an element X by taking the supremum over all norm-bounded tau continuous functionals. And typical examples are, as previously discussed, the space of bounded continuous function with the supremum norm and the compact open topology. Another example is the space of bounded linear operators equipped with the strong operator topology. And the third example is the dual of the Banach space equipped with the weak star topology. Okay, and now we are able to define what a bicontinuous semigroup is. By definition, a semigroup of bounded linear operators on a Banach space X is called bicontinuous with respect to some locally convex topology tau, satisfying these previous assumptions if the following conditions hold. First of all, TT is strongly tau continuous, so it's not non-continuous but tau continuous. So the orbit maps are tau continuous. Then it's exponentially bounded in norm. And three, TT is so-called locally bi-equicontinuous, meaning that if I have a norm-bounded sequence which tau converges to zero, and TTXN also converges to zero uniformly on bounded intervals. And to give a rough idea what are typical examples, let me list some here. First of all, the left translation semigroup on CB of R. This is not strongly continuous. Take the function sinus of x squared, then you can see that function is not strongly continuous with respect to the supremum norm, but it's bicontinuous if you add the compact open topology. In the dual semigroup on the dual Banach space, this is bicontinuous with respect to the weak star topology. And a very nice example actually is the implemented semigroup, which occurs mostly in quantum mechanics or quantum physics. So implemented semigroups on the space of bounded linear operators, I multiply from the left with a C0 semigroup and from the right with a C0 semigroup, and this gives rise to a bicontinuous semigroup, which is bicontinuous with respect to the strong operator topology. Okay, just to mention a few other also semigroups induced by flows are examples of bicontinuous semigroups. The Ornstein-Uhlenbeck semigroup on the space of CB of H, where H is a Hilbert space. And in the case of a bicontinuous semigroup, as in the case of C0 semigroups, I can define a generator. And the generator A of a bicontinuous semigroup is just defined to be this limit, but in comparison with C0 semigroups, I take the tall limit, not the norm limit. And the domain consists of all x and x, such that this limit actually exists and that this norm bounded. And you have to impose this, otherwise weird things in the domain can happen, and yeah, you don't want that. And actually this generator has really nice properties, like almost in the case of C0 semigroups. And we will need this later on, because now we actually want to talk about positivity and perturbations. So in perturbation theory, the general problem is the following. Let A be a generator of a semigroup, and consider another second operator B with the domain DB. And the question is, find conditions such that the sum A plus B on a reasonable domain generates again a semigroup S of T. And in this talk, we restrict ourselves to the case of Miyadera-Voigt perturbations. So we consider operators B where the domain of B coincides with the domain of A. And in the C0 semigroup case, it was considered by Miyadera in 1966, and later on by Jürgen Voigt in 1977. And for bicontinuous semigroup, Miyadera-Voigt perturbations were considered by Budde and Cauchy in 2004. And now we add an extra assumption, namely the positivity. So I have a positive semigroup, another operator. The question is, when does A plus B generate again a positive semigroup? So for positive C0 semigroups, positive Miyadera-Voigt perturbations were considered firstly by Dash and later on by Voigt in 1989. And we will do this now for bicontinuous semigroups, just to remind ourselves of some well-known facts. X is a Banach lattice if the absolute value of X is smaller than or equal than the absolute value of Y, then so behaves the norm. And the set of positive elements of X, the Banach lattice, will be denoted by X plus in what follows. And the bounded operator T is positive, and it's denoted by T bigger equals 0 if T of T applied to X is positive for each X, for each positive X. And a linear operator is called resolvent positive if there exists an omega in R such that a part of the real line of the positive of the real line is contained in the resolvent of A, and the resolvent is a positive operator for each lambda bigger than this omega. And as a matter of fact, one can prove, or it has been proven by Farkas, that a bicontinuous semigroup with generator A is positive if and only if this operator, its generator, is resolvent positive. And just to remind ourselves, X is called an AL space or an abstract L space if the norm of the sum is the sum of the norms for each positive for each two positive elements. Okay, and there's the positive Miyadera-Voigt perturbation theorem for C0 groups, C0 semigroups, sorry, due to Voigt. And the following: let E be an abstract L space and A a generator of a positive semigroup on E. Let B a positive operator and assume that A plus B is resolvent positive. Then A plus B is actually the generator of a positive C0 semigroup. And we want, or the goal of this talk is to invent a similar result for bicontinuous semigroups. And for this, we need some notions. This is the first definition for eta bigger 1. We call a subset D of X eta bidense in X for if I consider a bicontinuous semigroups with respect to a locally convex topology tau. If for all X in X, there exists a sequence in D which converges to X with respect to this locally convex topology tau. And furthermore, the sequence Xn is norm-bounded by a multiple of the norm of X. And this is called eta bidense. And the bounded function f from 0 to t0 for some t0 bigger 0 into the bounded linear operators is called local if for all p and p, so for every seminorm, generating seminorm, and for every epsilon bigger 0, there exists a constant k positive at another seminorm, generating seminorm, such that for all t in this interval and every x, one has this equality. So more or less, roughly speaking, you can take out the ft, the function f, out of the seminorm for the cost of an additional norm at the end. And this is important to know because you have this Miyadera-Voigt perturbation theorem for general bicontinuous semigroups due to Farkas, and it says if TT is a local bicontinuous semigroup and with generator A, and suppose the domain is eta bidense, and let B an operator from the domain of A equipped with a locally convex graph topology into X, which is continuous on bounded sets of D of A, and suppose that there exists a number T0 bigger 0 and an M between 0 and 1 such that this map is bounded. You have this estimate for the integral, which reminds of the original Miyadera-Voigt perturbation theorem for C0 semigroups. And the third condition is that for all epsilon and every p, there exists a q such and a k such that this estimate holds. So, and here at the end, you can imagine why localness of an operator will be important later on. And under this precondition, this operator B is Miyadera-Voigt admissible, which means that A plus B on the domain of A generates a local bicontinuous semigroup. Okay, and we need also a pendant for AL spaces because we have two topologies. So this is what I call a bi-AL space, or bi-abstract L space, if you want. And this is actually AL space, so the norm of the sum is the sum of the norm for positive elements. And there exists a subset of the generating family of seminorms such that P plus still generates this topology, and it's also additive for positive elements. And then you can prove the following theorem from Miyadera-Voigt perturbation theorem for positive bicontinuous semigroups, that eta be bigger 1 and A in generator of a positive local bicontinuous semigroup on a bi-AL space with eta bidense domain D of A. Let B be a positive operator and assume that this operator is also local and that A plus B is resolvent positive. And A plus B is the generator of a positive bicontinuous semigroup. So what you need as extra assumption in comparison with the original theorem due to Voigt is that this operator is local. So the localness is important here. And I try now to show how this works as an example on the space of bounded Borel measures. So in fact, every bicontinuous semigroup on CB of omega, where omega is a Polish space, actually gives rise to a bicontinuous semigroup on the space of measures with respect to the weak topology, weak star topology. This is just taking dual with respect to the weak star topology, what I mentioned in the beginning. And surprisingly enough, the converse is also true. So if I have a bicontinuous semigroup on M of omega with respect to the weak star topology, there is actually a bicontinuous semigroup on CB of omega, such that this dual coincides with this original semigroup. So the norm of on M omega is just the total variation norm. This is an AL space, and tau is generated by so the weak star topology is generated by these semi-norms, and actually you can restrict yourself to all positive functions here, and the locally convex topologies tau plus and tau actually coincide. Okay, let's continue with Cauchy and differentiable measures. About differentiable measures we will hear later on in room A again. So take omega to be R and define the centered Cauchy measure by this. So this is more or less the multiplier of the Lebesgue measure. And for measures, one can define the convolution by this. So it's similar to the convolution of functions. And on TT, defined by T of 0 to be the identity on the space of measures, and T mu is the convolution of the centered Gaussian measure with this actual measure. And one can show that this semigroup is actually the adjoint of the Gauss-Weierstrass semigroup, or the heat semigroup, if you want. So this holds. And for the Gauss-Weierstrass semigroup, the generator in one dimension is just the Laplacian, so the second derivative. So you have in mind that this might be the case in the measure scenario, but then you have to be aware what differentiable measures actually mean. And the Borel measure on R is called Scoreheart differentiable. If for every bounded continuous function, this function is differentiable. And there's a theorem that says let U be mu a Scoreheart differentiable Borel measure, then there exists a Borel measure, which is its Scoreheart derivative. So this satisfies this. And this can, for example, be found in the book of Bogachev. And now we consider positive perturbation with the notion of differentiable measures. One can actually show that the generator of this semigroup is the Laplacian in the measure sense. So you take the second Scoreheart differential derivative, and D of A consists of all measures which are twice Scoreheart differentiable. Okay, and now let psi be a fixed positive unbounded Lebesgue integrable function, and define B to be the scalar multiplication of a measure. And then there exists actually a function such that this holds, so we have a local operator, and you can show that the solvent of A star, A sub star, which is the generator of the Gauss-Weierstrass semigroup, satisfies this inequality, and therefore one can show that, or conclude that BR lambda A is local, and you have BR lambda A is smaller than 1 if lambda is large enough. And so A plus B generates a bicontinuous semigroup, which is actually positive. And before we come to an end, just let you know that there's the 8th European Congress of Mathematics from the 20th to the 26th June 2021. And together with David Seifert from Newcastle, we organize a mini symposium on operator semigroups and evolution equations. And if you're interested to give a talk, you're more than welcome to register and to submit your abstract. But please do this before the 1st May. We would like to see some contributions of you in our mini symposium. And yeah, thank you very much.
Thank you very much for very interesting report and for very interesting information. Questions, please.
Christian, can you show us the list of literature once again?
Yes, sure. So this is where I got these differentiable measures from. It's the book of Bogachev. This positive Miyadera-Voigt perturbation. This is an online first version in positivity, and this is the reference for Miyadera-Voigt perturbations for bicontinuous semigroup from Farkas. This is the original PhD thesis from Franziska Kühnemund, and this is the article from Jürgen Vogt in the Semigroup Forum.
And then I have a question: which literature do you recommend concerning semigroups on the sets of on the space of measures? C0 semigroups.
C0 semigroups on the space of measures.
Yeah. Or you just start with bicontinuous semigroups and there was nothing before? Yes, there should be something.
More or less, yeah. So I really concentrated on the bicontinuous part.
Okay. Okay. If you find some good reference, please let me know.
Yeah, we'll do so. Definitely.
Yeah. Okay. But probably C0 semigroups are not enough, and bicontinuous are more relevant. Yeah. So thanks for the talk.
You're welcome, Jana. Thank you.
The questions, please.
Yeah,
very
please,
positive talk. Thank you.
Do you, I mean, this local condition on BR lambda, it is really needed, or do you have a counterexample? Or maybe you can also, while one can probably not say why you need this condition, but yeah, exactly this.
You need this estimate actually, and this is to get this estimate for the for the semi-norms. You actually need this local condition, but I cannot think about a counterexample spontaneously.
Yeah. I mean, a resolvent positive alone does not suffice. This on AL spaces. This is true, but yeah, okay. But because in the Banach space case, you don't need such a condition. I mean,
but I guess because you have to deal with two topologies, so this local condition actually means that it is an operator which is Tau continuous on bounded sets, or non-bounded sets. This is what this local condition actually translates to.
Okay.
I hope this answers your question at least a little bit.
Yeah.
Thank you. Other questions? I have a question about the sum of two generators of bicontinuous semigroup. Does some analogs of Trotter-Kato or Chernov theorem exist for this sum?
Yes, and Franziska Kühnemund and some other works.
Yeah. Actually, what Jana says, so it's comparable with the classical theorems for C0 semigroup, plus some additional regularity assumptions. But this also you can find it in the PhD thesis from Franziska Kühnemund or in one of her articles.
Albanesa Mangino or something like this.
Yeah.
Yes.
Yeah, that's true.
There is a paper which is later than the PhD thesis of Franziska Kühnemund about Chernow theorem for bicontinuous semigroups.
Yes.
Yes. Yes, of course. It is very fruitful approach to the approximation of semigroup. And Christian, thank you very much for very interesting report. And now we can finish